Artificial intelligence can pass the bar exam and write complex Python scripts in a matter of seconds. But ask those same models to simulate a bouncing ball, and they often fail, clipping through solid geometry or ignoring gravity entirely. Large language models succeed because they have a near-infinite supply of text and images to learn from. They simply ingest the existing, easily accessible data already sitting on the open internet. Teaching a computer how the physical world operates is different. Physics requires spatiotemporal data, highly precise mathematical records of exactly how complex materials and elements change across both space and time. This comparison shows the core bottleneck in training physical models. Because spatiotemporal data isn't just lying around on the internet, researchers have to run massive, computationally expensive numerical simulations from scratch, resulting in a painfully slow drip of data for training. The current roadblock to physics AI is a data gap. Without a unified, large-scale training infrastructure, models lack the diverse examples needed to learn physical behavior reliably. To solve this data drought, a coalition of researchers from Polymathic AI, the Flatiron Institute, Cambridge, and Princeton teamed up to stage an intervention. Their solution is called The Well. It is an open-source data repository designed to give machine learning models the depth of training required for physics simulations. The collection holds 15 terabytes of data. This volume provides a standardized foundation that dwarfs the isolated, fragmented files individual researchers have been forced to rely on for years. By open-sourcing a collection of this magnitude, The Well takes the burden of generating physics data off the individual researcher and establishes a global pipeline for model training. The Well is an aggregate of 16 distinct datasets. Together, they cover physical phenomena across a vast range of scales. At the smallest scale, the data covers abstract cellular biology and acoustic scattering, mapping how organisms and sound waves react to microscopic stimuli. At the human scale, the repository tracks spatiotemporal fluid dynamics. It maps the chaotic interactions found in wind tunnels or rapidly churning water currents. Scaling up to the cosmic level, the repository includes magnetohydrodynamic data, allowing models to study extragalactic fluids and simulated supernova explosions. Storing this volume of spatiotemporal data requires massive capacity. The smallest individual dataset in the repository requires nearly 7 gigabytes, while the largest demands over 5 terabytes. Training across these diverse datasets encourages AI models to identify shared physical patterns across different domains, rather than overfitting to one narrow scientific scenario. Having terabytes of physics data is only useful if machine learning developers can efficiently get it onto their machines. The package is built for rapid deployment. Engineers can pull it directly from PyPy or build it from source, utilizing specific flags to ensure the code takes full advantage of their local CUDA hardware acceleration. This flowchart illustrates navigating the extreme storage footprint. Lacking 15 terabytes locally, engineers stream datasets directly from Hugging Face. Once flowing, the repository becomes an integrated testing ground. Developers use Hydra configuration files, like local.yaml, to rapidly swap training scripts without rewriting core code. To get developers started immediately, the repository includes pre-trained baselines. Out of the box, researchers can run a Fourier neural operator, a specific architecture for physical equations, directly on the active matter dataset. By combining the raw scientific data with the configuration files needed to process it, researchers finally have an even playing field to accurately compare competing AI architectures. The creators of The Well include an explicit warning about those preloaded checkpoints. The included baseline models are intentionally basic. They are not the current state-of-the-art for surrogate modeling of partial differential equations, the mathematical formulas used to describe how physical systems evolve. Those simple baselines serve as a starting line. The Well is an open gauntlet thrown down to the machine learning community. Study the benchmarks, use the data, and build new architectures designed specifically to beat these results. Mastering these spatiotemporal benchmarks will trigger a significant leap forward in our ability to model climate change, test aerospace designs, and simulate deep space phenomena. These 15 terabytes of code provide the fundamental infrastructure necessary to build physics-literate artificial intelligence.